Yeah.
Yes. Is it recording? I can't tell.
I can't tell either. Yes, it's recording.
Yes, it's recording.
Good.
Great. Okay. Cool. Right. Well, thank you very much for coming, everyone. This is, as I mentioned to the people who are early into the room, this is a talk based on a workshop talk at FMAI last month. The talk length was only about 15 minutes. I've padded it up a bit, so it may be a bit longer than that, but it's certainly not, 45, 50-minute talk like we're usually used to. So if people want to interject and have a discussion about things that I gloss over rather quickly, please do feel free. Cool. So the title of this talk is Neural Network Robustness, Careful What You Verify. And basically it's describing some of our recent work with the lab that was looking at trying to embed arbitrary constraints into neural networks. And in particular, doing this via logical constraint-based training. So the idea of this is to automatically express the properties that you would like of your neural network in logical formulas, for instance, first-order logic, and then automatically translate them down into a semantic preserving loss function that can then be used in training, and the loss function should help guide the neural network training process to fulfill the constraint. So a very, very simple example here, suppose you have some neural network F, and you would like the output of F to always be less than or equal to 10. Well, you might generate this extra loss function that encodes this constraint that takes the difference between f of x and 10, and then adds that as the loss. So initially, we wanted to assess how effective these existing solutions to this problem were, and in particular DL2, which I'm sure some of you have heard of, which was published a couple of years ago, which used first-order logic, kind of subset of first-order logic, with support for single universal quantifiers. And in order to compare how effective it is at translating arbitrary logical formulas, well, you want to try and compare it against techniques that already exist. And in particular, we thought a good way of doing this would be to look at neural network robustness, because there are a lot of very specific training techniques to maximize neural network robustness. So we wanted to see how effective, and obviously they can be specialized and tweaked and tuned specifically for neural network robustness. How effective is the general approach at training for robustness compared to these specific techniques? So I'm hoping many of you have seen these famous robustness examples before. For those of you who haven't, neural networks are great at, neural networks currently using current training techniques are really good at learning the right answer most of the time. But occasionally when you take an image which it knows the answer to, and you add a little bit of noise to it, an imperceptible noise to a human, then the classification of the neural network can completely flip. And it can output something, for instance here, it can say this picture of a panda is actually a given with very high confidence. So the idea of robustness is that if you change the input only by a very, very small amount, then the output should also change only by a small amount, which obviously isn't the case here. It's you've changed it by a small amount and the prediction has flipped by greater than 50%. And neural networks are well known to be not robust, and there's a ton of literature on this. And in particular, there's lots of attacks out there for generating these perturbations, which lead to these adversarial examples. And an instance of the noise, such as this, is known as an adversarial attack or an adversarial example. So we came and started looking at existing techniques for improving robustness. And one of the common formulas for robustness is this one, which says that if you have some training sample in your training data set, x hat, then for any x, the distance between x and x hat is less than epsilon, then the distance between the output of the neural network and the true label in the training data set y is less than or equal to delta. So this exactly encodes the notion that a small change in the input results in a small change in the output. However, we then, as we were looking through the literature, we noticed there are a few more definitions of robustness, like this one, and this one, and this one, and this one, etc. And it was kind of bewildering that there were quite so many different definitions. And as someone who comes from formal verification subfield, it's kind of worrying, really, that there's so many different definitions, and in particular, they're not discussed widely in the literature. People generally pick one without any justification in particular, and we haven't seen any discussion of the differences between these different definitions. You know, what are their assumptions? What are the different assumptions between them? What is the relationship between them? Do some imply the others, etc., etc. And to make matters worse, okay, there's all these different logical expressions for robustness, but we haven't even started to consider the notion of distance. That we're using a small distance, you know, if output only changes a small amount, what does small mean? And there's many different definitions of smallness, and it's an active research area. But when combined with all the different logical formulas and then all the different notions of distance, you actually get a huge explosion in the number of different definitions of what a neural network being robust actually means. So we were hoping to bring some clarity to this.
Matthew, sorry, may I interrupt you?
Yeah.
Do you want to maybe quickly explain to everyone what these logical formulas stand for, why there are so many definitions?
What do you mean by that? What each individual one means?
It's just, I'm not sure. Yeah, exactly. I'm not sure everyone in the team exactly knows why, you know, even these 5, 6 exist.
Indeed, I'm coming to this in later slides.
Okay, fine.
Yes.
Okay.
Sorry, this is just to try and illustrate the problem that there is a huge number of these things.
Okay, cool.
So, so how did all these different definitions arise? And the answer is that they tend to arise from different training techniques. And some of the common training techniques are things like data augmentation. So if you want your neural network to know that the solution is, you know, it's always a panda within, you know, any image that is close to the panda image in your data set, well, you might generate a little bit of noise and add it to the original panda image, and then add that to your data set. So you might do this 5 or 10 times, and you might generate, for each training point, you might generate multiple copies of your training data set image with a little bit of noise added to them. The next technique is called adversarial training, which is when you try and tweak the loss. You keep your data set the same, but you try and tweak your loss function, and in order to maximize robustness, which we'll come on to. And then there's things like Lipschitz robustness training, which is training for something called Lipschitz robustness. And again, there's a separate set of techniques for that. So we can go through these one by one and have a look at how these different logical formulas for robustness arise. So adversarial training is the first one, which was originally proposed very soon after these adversarial counterexamples to neural networks were discovered by Goodfellow et al. And instead of minimizing the standard loss function, they instead try and minimize the maximization problem of trying to find the point within the ball, epsilon ball, the region which is a small distance away from your original training data sample. And they try and find the worst possible point in that region, so the one that maximizes the loss. And how they go about solving this maximization problem is, again, an open research question, and, well, not open research question, is a research question, and there's many different proposals. The current most popular ones are things like gradient descent, which again uses the gradient to try and explore the epsilon ball, and it's called the fast gradient sign method. And if you squint very closely, this is actually trying to minimize the value of delta in the following definition, which is exactly the standard definition of standard robustness we had earlier, which is saying, well, you're never going to drive, you never actually want your loss function, the loss function, to be exactly equal in the whole region around your training data image, right? Because if it was exactly the same, if it always output exactly the same value in the whole of this region, then in fact it's never actually changing. It can never actually change its mind, right? There's got to be some gradient on the within the epsilon ball. So we say, well, what's the maximum acceptable gradient, and we're going to call that delta. And if you take the loss function to be the notion of distance in the right-hand side of implication, you get exactly this, which is which is what we're calling standard robustness, which is for x, if the distance between x and x hat is less than or equal to epsilon, then the distance between f of x and y is less than or equal to delta. Is everyone vaguely happy with that? There is a little bit of sleight of hand here because we are the distance function on the right-hand side, as I said, is the loss function, the original loss function that was being used.
I'm sorry, Matthew, just quick question. Does that mean that if the input is perturbed by no more than a small value, and then you will watch whether the output will be, how the output will be changed, right? It's not you are perturbing the output, the output will be changed. The output will be changed, right? It's not going to be, it's not going to be identical, but the difference between the output and the true output label, you want to be less than or equal to delta. Okay.
So it should only be changed by, it should only change by a small amount from a true label.
This is also related to the uncertainty, of a neural network, right? So I will ask this later. Sorry. Okay.
No, you can ask now if you want. There's no problem.
Yeah, there's a neural network. You can actually use Monte Carlo, simulation to calculate the uncertainty.
Yeah.
Is MCM using the chop out, right, to get a probability of the output.
Yes.
And then okay, all right.
Yeah.
So
yeah.
are you going to do this, or you are thinking about, have you think about this?
So we're more interested in the actual logical definitions of the properties of these logical definitions, rather than how you go about implementing them. I guess we're just trying to motivate how these come up with. One of the common approaches, which is exactly along those lines, which is viewing it from a probabilistic perspective, is that you can actually improve the robustness of these neural networks by taking an ensemble approach, where you feed in lots of inputs into it and then somehow take the average of the outputs. And that actually improves robustness, which I think is exactly the kind of Monte Carlo sampling of the
I think there's also a new, not a new work, it's like from Cambridge. What they do is they use the chop out, to chop out the weights within the neural network. And then they can get some output, and then they can get some insight into the uncertainty of the neural network. So I think, okay, we can talk about it later.
No, sounds good. Definitely be interested.
Can I just suggest one thing, maybe so that to make sure that everyone is absolutely on the same page, let's just go very quickly through what these XX hats and so on are. So X hat is your initial panda, and X is your anything in the region like perturbed panda, right?
Yeah.
FX is what the neural network outputs for any image, perhaps perturbed, and Y, on the other hand, is an output that the neural network gives for X hat.
No, Y is the true label for X hat in the training data.
Okay.
F of X is the output of a network on the perturbed image.
Okay, so you're making some assumption then on what the output is. It's class.
Well,
rather than probability over.
Yes, so not necessarily its class. I mean, it can be whatever output. I mean, if it's a regression task, it can be its regression probability.
Matthew, can I ask, when you're talking about that, then does Y have to be a known ground truth, or could it be like an output that you've got and then you're testing it against other perturbed outputs?
So this is a very good question, and this is yet another dimension to the definitions that I haven't mentioned and wasn't going to mention in this talk. But yes, you have a choice. You can compare against, if you have a training data, a labeled training data set with, like I'm assuming here, where you have pairs X hat and Y, where Y is the true label of the training data X hat, then you can use this definition. But you can also compare it, instead of doing the loss between f of x, and instead of comparing the distance between f of x and y, you can also compare the distance between f of x and f of x hat. So the output of the network on the original training data point rather than the true label, and that leads to a different definition and slightly different properties. And indeed, that's often desirable to use f of x hat instead of the predicted output on the original training sample, rather than its true label when you're using these logical semantic-based constraints, because usually you have the original loss function as well as your loss function that penalizes robustness, and your original loss function will already penalize deviations from the true label y. So you want your property-based loss function, your robustness component of the loss function, to actually just penalize the difference between its true output, between its current output for the training data sample, rather than its output for the true label, which is always already being penalized by the original loss function.
Okay, team, we're just then holding on to the end of this talk. We remember x hat is something that comes from the data set, and y is its label, whereas whenever we see x, it's just arbitrary image.
Yeah.
Good. Okay.
Cool. So the next augmentation scheme is the next robustness training scheme is data augmentation. And again, as I discussed earlier, prior to training, so before you do any training at all, you generate new training data samples close to the existing data and label them with the same output as the original data. So again, you still have this notion of closeness in the input space. So you still have, for all x, you're still looking at generating training data, which is no more than epsilon away from your true training data sample. But actually, by labeling them with the same output as the original data, you're actually assuming that they are of the same class. And this is, sorry, I should say this is particularly used, data augmentation is usually used in a classification setting. So you have your output of a neural network as a class, a discrete class rather than a probability distribution, say. And by labeling them with the same output class, you're in fact saying that the maximum, sorry, I'm not explaining this very well. Let's try again. Let's restart. Classification robustness. In a classification problem, your network f of x usually outputs a probability distribution over the different classes. And in order to generate the final answer, you usually take the class with the maximum probability. So this is argmax of the f of x. And when you're adding new samples with the same label as original, what you're saying is that every single point in this epsilon ball should have the same label as the output. You're not saying that it shouldn't differ by a little bit. You're saying that the output label should be exactly the same, which leads you to exactly this definition down here, which is classification robustness. So is everyone happy with the difference between classification robustness and standard robustness? Standard robustness is saying there can be a little bit of wiggle room in the output, whereas classification robustness is saying there's absolutely no wiggle room when you take the maximum class. Your maximum class over your output probability distribution has to be equal to the original label. Cool. Literate robustness is a stronger version of standard robustness. and it's actually saying that when you perturb the input by epsilon, the output again can be perturbed a little bit, but the size of the output perturbation has to be proportional to the the size of the input perturbation. So in particular, if the difference between the generated panda, the noisy panda image, and the original panda image is that value, then the size of the change in the output has to be no more than L times the size of the perturbation on the input. And as we'll see, this is actually a stronger definition of standard robustness, and there's a nice graph that I have in a bit that explains the graphical interpretation of this. Probably should have added it here. Cool. So we now come back to logical constraint-based training, which I was talking about in original, which is the idea of translating these constraints, arbitrary constraints expressed in some subset of first-order logic, down to loss functions. And it turns out that logical constraint-based training can train for standard and Lipschitz robustness, but actually it can't handle classification robustness. In particular, as the argmax function provides no useful gradient on which to train for, right? An argmax function is just, it's got zero gradient everywhere except the discontinuity points. So you can't actually generate a loss function that is going to help you try and maximize this. So in the original DL2 paper, Fisher et al. Actually proposed an alternative to classification robustness without a whole lot of discussion about it. In fact, there was no discussion about how it differed from classification robustness, but this is how they got around this problem. And we're gonna call it approximate classification robustness. And this says that if the correct classification class from your output, from your labeled training data, should always have a probability of at least some value eta. And usually eta is 50% or greater. So it says that if you perturb your image by a little bit, then the true label's probability never dips below this value eta. So we're just going to look at these 4 different definitions of robustness, and we're going to try and do a comparison of them. The first point we're going to look at is a gradient available, which actually we've already discussed. The gradient, you do have a gradient for approximate classification robustness and standard robustness and Lipschitz robustness, and therefore you can use logical constraint-based training for them, but you don't have it for classification robustness. So that, I guess that's a downside of classification robustness, using classification robustness. The next one is a logical relationship. Do any of these definitions imply each other? So if, for instance, if you're standard, as we'll see, if you're standard robust, if you're standard robust, you're also if you're Lipschitz robust, you're also necessarily standard robust. And what relationships are there? What assumptions do they actually make about the training data? We're going to find that actually classification robustness does make assumptions about the training data that's in your training data set, which is interesting, and it's not necessarily immediately obvious from the algorithm. And finally, we're going to compare how interpretable these definitions are. So do they actually give you an insight into what your neural network is doing underneath? Priya has raised her hand. Go for it, Priya.
So I was going to ask, does the application domain come into picture when you discuss, because what it means to be robust could depend on what application domain.
So I am sidestepping that. You're absolutely right. It does depend on, robustness does absolutely depend on what problem you're trying to solve. And this actually comes in, from my perspective, I know that others disagree, but this actually comes in at the distance function level. So we currently don't know how to, my feeling is that as a community, we don't currently know how to come up with good distance functions, that we tend to resort to things like pixel distance between pixels, when actually our distance function should embed some semantic properties about our task. So for example, if you were trying to classify road signs in an autonomous car, then not only would you want your neural network to be robust against small changes in individual pixels, you might want your neural network to be robust to the color of trees. So if it's different season and your tree, the same tree, same image, and your tree, or even robust, well, this is a bad example because you should be robust to whether your trees exist in your image or not. Maybe a better one is the sky color. So if your sky is gray versus your sky is blue, that's a huge difference on the pixel level between your images, but your distance function should assign images, exactly the same image with different color skies as being close together. But we don't know how to do that yet necessarily in a systematic way. So that's where I think the domain specific nature of robustness comes in. It's encoded in distance function, which I'm not planning to discuss in this talk, but it is absolutely a problem. And but the things that I discuss hold regardless of whether your distance function manages to capture these domain specific notions of robustness or not. Does that make sense?
Yep. Thank you.
Cool. Okay, so the first one, as I've been saying, Lipschitz robustness, if your Lipschitz robustness is a strictly stronger property than standard robustness. So if you're epsilon L Lipschitz robust, then you're standard robust with epsilon and epsilon times L, but the converse isn't hold. And it's very easy to see this graphically. So what standard robustness says is that if you perturb your X value by no more than epsilon, so between, for example, on the between 0 and epsilon on these axes, then the Y value changes between 0 and delta. And as you can see, this function is this very simple function, possibly not a neural network, is standard robust. Because no matter how much you change X between 0 and epsilon, it's always less than delta. Lipschitz robust says that if you perturb your input by some value between 0 and epsilon, then your output must change by no more than a value that is proportional to your change in your input. So the L parameter essentially encodes the gradient of the change that you're allowed. And as you can see that it's fairly obvious from this graphical demonstration that if you're Lipschitz robust, then you must also necessarily be standard robust. But the converse doesn't hold, right? This is a function that is epsilon delta standard robustness, but it's certainly not, there's no value that is Lipschitz robust, for which it is Lipschitz robust. Yes, so so if your network is Lipschitz robust, then it's also necessarily standard robust for some value of delta, which happens to be epsilon times L. As we mentioned earlier, we have, as you would hope, you would have a relationship between approximate classification robustness and classification robustness. And it is that when your value of eta, so when your threshold for the true class is greater than 0.5, then if your true class, the true output label class is greater than 0.5, well, then necessarily the output image must be classified as that class. So you have this very simple relationship here, which is what we'd hope, because we were trying to approximate classification robustness. So we want our approximation to be sound, so that when the approximation is true, we always have the original property is true. So there is, interestingly, there is no relationship between standard and classification robustness. And indeed, between Lipschitz robustness and classification robustness, and each of it, basically standard and Lipschitz robustness form a pair, and classification and approximate classification robustness form a pair. And there's no relationship, there's no logical relationship between the two. And we're going to try and illustrate this graphically. So imagine we have our input space, which is the big rectangle. So this is all the possible data values, all the possible inputs that we could feed into our neural network. And we have the data manifold, which is in blue, which are all the inputs that are actually realistically going to occur. So these are the inputs that the neural network is actually going to see during operation. Now, if we're trying to verify that a property holds over the neural network, I mean, ideally, we only really need to verify it over a data manifold, right? Because it's never going to have one of the points outside the data manifold fed in. So we only really care about verifying property over the data manifold. Now, unfortunately, if we don't know the shape of the data manifold, right? If we knew what the data manifold looked like, then we wouldn't need to use a neural network in the first place. So how do these algorithms work? Well, they approximate the data manifold by taking these epsilon balls around each of the training data samples, which are the x's, and they verify that the property holds within each of these epsilon balls, each of these little circles, and then they argue that this says, well, if it holds in lots of these epsilon balls, then hopefully it kind of holds our entire data manifold. Well, perhaps that's a little bit disingenuous. Maybe they don't argue that, but it's the best that we can do. And the reason why maybe they don't argue that is actually this data manifold is an incredibly high dimensional space, usually for most tasks. And your training data is only going to sample an incredibly small value of it, a small fraction of that high dimensional space. And even if you take epsilon balls around your training data, what happens is the curse of dimensionality means that your epsilon balls even your epsilon balls are not going to give you a very good coverage of your space. So we are verifying that the neural network has this robustness property, or indeed arbitrary properties, within this subset of the data manifold. But it's interesting. It's maybe not verification in the sense that is used in other fields, because we're not verifying it for all inputs, right? You're only verifying it within this subset of inputs. So is it that even when we can prove that it's robust within these regions, is it actually robust? Not sure, but even the state of the art is still focused on verifying this sort of stuff. So let's now look at a classification task where we have two classes, purple and yellow, and the color on the data manifold indicates the probability of it being classified. So at the top end, we have the purple objects, and at the bottom, we have the yellow objects. Now, what does standard robustness say? Well, standard robustness says that within one of these epsilon balls, the output probability doesn't change very much. And indeed, we can see that that is true, right? We can take any epsilon ball, and the color is pretty much uniform. It's not entirely uniform, but if we take a value of delta to be reasonable, then we can say, yes, it doesn't change very much within each of these epsilon balls. On the other hand, if we take classification robustness, i.e. we threshold it, and we say, we're now looking at a classification task, and we want the answer, is it purple or is it yellow? So we draw this hard line down the middle, which represents a 50% line, 50% probability. So if it's greater than 50% probability of being purple, it is purple. If it's less than 50% probability of being purple, it's yellow. And we now look at classification robustness. Classification robustness actually says that no, these points in the center along the decision boundary are not robust because the classification changes within the epsilon ball. So you can actually see, and likewise, you can come up with an analogous picture where if you can have points which are classification robust, but are not standard robust. Which I didn't add in the original talk, so I have 15 minutes, but maybe we can discuss those in a minute. This problem actually gets kind of worse though, because imagine that these epsilon balls actually overlap. So here we have two data points neither of which are classification robust. But in this area, this red area here, the property, actually we have conflicting specifications. Our definitions of robustness actually conflict, because in this ball, upper ball, we said that the output has to be purple according to our specification, but in this lower ball, the output has to be yellow. So we actually have our robustness definitions is actually inconsistent. So what is the assumption underlying here? Well, our assumption when we do data augmentation and when we are looking at classification robustness and saying that our classification doesn't change, we are implicitly assuming that the training data does not lie near decision boundaries. So maybe this is obvious, but we haven't found it discussed anywhere in the literature explicitly. And it's obvious in some sense, but there's also a tension here, right? Because remember what I said earlier about how the epsilon balls don't provide a very good coverage of our training of our data manifold for true underlying distribution of inputs. So ideally, we want to expand our epsilon balls to be as big as possible, right? So we get a good coverage. Maybe we'll have to expand delta as well, but we want to get a good coverage of the input space. But as we expand our epsilon balls with classification robustness, we get a higher and higher chance of getting a contradictory specification. And because we don't know where the decision boundary, the true decision boundary actually lies, then we won't know if we are generating a contradictory, whether our definitions are actually contradictory or not, whether we actually generate a clash like this. So we're saying that classification robustness should be used with care, and you should be aware that it is making this assumption about your training data, that it doesn't lie on decision boundaries, doesn't lie close enough to decision boundaries. Cool. Okay, so next point of comparison is interpretability, and how much insight does this give us about the neural network and the behavior of the neural network? And we're arguing that classification robustness is the most robust. Is the most interpretable. You have some notion of how much deviation is allowed in the input space, and then you're saying that the output must remain the same. So this actually gives you a good insight with how much you can move, how much you're allowed to move, and if you have a good notion of distance in your input space, then you can actually kind of visually in your mind's eye kind of work out how much perturbation is allowed before the neural network's answer changes. So classification robustness in that sense is quite desirable, and indeed we find there's lots and lots of papers, particularly in the classification literature, that use classification robustness despite its shortcomings that we highlighted in the previous page. Standard robustness is slightly less interpretable, but it's still meaningful in the sense that yes, you now have to have some notion of distance in the output space. But if you usually distance in the output space will have some meaningful semantics. So you can say, okay, I'm changing no more by epsilon in the input space, changing by no more than delta in the output space. However, Lipschitz robustness, although it's a really strong desirable property, and it's stronger than standard robustness and therefore more desirable, in that sense, it is also the least interpretable. Because what the parameter L does is it relates how much you can move in the input space to how much you can move in the output space. So it's actually a ratio between distances in the input space and the output space. Now, the problem is that the distances in the input space and the output space are almost certainly going to have completely different semantics. So if you're saying you're moving, if your input distance is a very naive, simple one, and you're simply looking at pixel distance, so you're saying no more than 10 pixels can change, and your output distance, your distance in the output space is, how much can probability distribution change? Well, it's very hard to relate the two, right? It's what is 5 times as much movement in the output space if L equals 5, what does there is 5 times as much movement in the input space allowed as in the output space actually mean? And it's very hard to actually assign semantics to Lipschitz robustness, even though it's a very desirable property. L doesn't tell you much. You can't assign any meaning to L in the vast majority of cases. So maybe Lipschitz robustness is, if you're trying to actually understand what your neural network does, then maybe Lipschitz robustness isn't the best one. Another thing that we noticed in this, when we were doing this work, is actually there's a very, very inconsistent in how people, the literature is very, very inconsistent in how people measure whether your neural network obeys the constraint. And there's lots of different terms for lots of different measures. And we thought we'd try and come up with a standard naming scheme for 3 notions that we think are the most useful to measure. So the first one is constraint satisfaction. And this is simply the proportion of regions, i.e. epsilon balls, in which a property holds. So if your robustness, if you're robust in 6, completely robust in 6 out of 12 of these regions, then you'd have a constraint satisfaction score of 50%. Yeah, hopefully that's intuitive. I won't go through the notation, seems, but yeah, it's simply measuring the number of epsilon balls in which a property holds. Obviously, if you have the contradictory spec, like in classification robustness, then you can never achieve a 100% classification, 100% constraint satisfaction score. The next one is constraint security, and this is saying, okay, well, we're not interested in, we may not be able to train the neural network so that we are guaranteed that this property holds in each epsilon ball. We may not even be able to actually verify if our property is complicated enough. So robustness, depending on our distance function robustness, we may not even be able to actually have an algorithm that checks whether the property holds in each epsilon ball. So a nice proxy for constraint satisfaction is constraint security. And this says it's how many regions, how many epsilon balls can an adversary find a counterexample to property P. So a common adversary might be the fast gradient sign method that we've found before, or PGD attack, which tries to exploit the gradient to try and find a counterexample of the property. And yeah, we're interested in, can an attacker easily find a counterexample? Obviously, this score will change depending on which attack you're using. But this is a good, and obviously it will underestimate constraint satisfaction because an attacker may not always be guaranteed to find a counterexample, even if the counterexample exists. But in the case where we can't actually verify the property, then constraint security is a good proxy. Finally, and the weakest of these is constraint accuracy. And this is the probability of randomly coming across a counterexample to property P. So this isn't looking at, there's no attacker, there's no one actively trying to find a counterexample, but in the probability in everyday use of a neural network coming across a counterexample. And what do we mean by randomly? Well, by default, you might take a uniform distribution over your data manifold, over the input space. In practice, if you have some domain knowledge, you might be able to come up with a better random distribution across the input space. You may know that some regions are more likely than others, and you can adjust the distribution that you're using to randomly sample. But yeah, so we think that these are the 3 metrics that you should actually report when trying to evaluate whether your constraint holds on these regions. I guess this is linking into what was said earlier about Monte Carlo simulations of trying to estimate the confidence of a neural network within each region. So, what are the conclusions? Lipschitz robustness is a very desirable property. Yes, I missed out a talking point. Ooh, okay. Let's quickly go back. So we have said that classification robustness is not desirable around the data manifold. You don't want to be classification robust along the data manifold. In contrast, actually, standard robustness is, you'd actually like standard robustness to be true everywhere, right? We are approximating it via this these circles, but you'd actually like it to be standard robust everywhere on the manifold and everywhere on the input space. Whereas classification robustness, you only want to hold locally within regions of the data manifold that are away from decision boundaries. So Lipschitz robustness is, as we said, and standard robustness is very desirable globally, but it's not very interpretable. Standard robustness is desirable, that you want it to hold over the entire input space globally, and it is moderately interpretable. Classification robustness is highly interpretable. It really gives you, you can really say strong things like neural network if you're classification robust, but it's only desirable in regions where you're high confidence, i.e. away from decision boundaries, and it makes the assumption that your data set does not lie close to decision boundaries. Items in your data set do not lie close to decision boundaries. Things that I haven't touched upon is, when are these conditions actually amenable to verification? When are these different definitions can actually be verified? When do we have algorithms to do it? What is the choice of distance function? As I said, we still don't know how to come up with good distance functions that encode semantic similarity or semantic distance for different domains. And there's various other considerations as well, which I haven't discussed. Cool. I think that's probably it. Thank you. Does anyone have any questions?
Thanks a lot, Matthew. Very good talk. That's the second time I see it, so I'm not very surprised, but yeah.